Hello everyone. In this video we're going to discuss integrals, otherwise known as the antiderivative. Now we have spent months learning how to find the derivative of pretty much any function that they give us, but now we want to go backwards. If we are given a derivative, can we find the original function? And this process is called antidifferentiation or integration. Now the red that you see in front of you is the official definition. If you have a capital F, which would be the result, the antiderivative, and you take its derivative, then you should get the original function. Another way to think about it is that the integral, and that is what that weird skinny s symbol is, the integral of the original function, and dx is part of the notation for integrals, should give you the capital F, and that's the notation part. So one way to think about this is literally going backwards. So let's look at this first example here. Based on what we know about the rules for differentiation, can we go backwards for 3x squared? So think about it this way. The derivative of what will give you 3x squared? Just thinking backwards. Well, if you think about it, then 3x squared looks a lot like the power rule. If we wanted to take its derivative again, that's what we would use. So if we go backwards, we would be going up a power, and the exponent would go out front. So if we're going backwards, then we would go up a power versus down a power. So what about the original being x cubed? And we can check this using derivatives. So if we take the derivative of x cubed, the 3 would come out front and we would go down a power, exactly the result that we got. So this is how antidifferentiation works. You're literally going backwards. So for this next one, the derivative of what will give you sine of t? Well, going through your head, the derivative of sine is cosine. The derivative of cosine is negative sine. So the derivative of cosine would give me sine, but the derivative of just cosine would give me negative sine. So if I have a positive sign here, it's the only way to get positive sine would be if I did negative cosine. So that's how this works, is we're literally going backwards. So for our next example, it's not really an example. We want to derive a formula for going backwards for the power rule. Well, think about it. The power rule for differentiation, you're going down a power and the exponent comes out front. So if we're going backwards, instead of multiplying, we're going to have to divide, and instead of going down a power, we're going to have to go up a power. And you'll always have this dx every time. So we're going to end up dividing instead of multiplying, and we're going up a power. And the last thing is something I haven't mentioned yet, and it's that every single time of these we're going to be adding plus c. And the reason for that is if you're finding the derivative, well, the derivative of any constant, let's say we had the x cubed plus 4, well, that'd be the 3x squared and then plus 0. The derivative of a constant is 0. So we actually don't know if we have a constant in the original function or not. And that is where this plus c comes in. Because we are going backwards, and 0 is the result, we don't know if constant is above it. So these first two examples are actually wrong, because each one of them needs a plus c. So the antiderivative of f of x would be x cubed plus c. The antiderivative of g of t would be negative cosine t plus c. This arbitrary constant must be there if you're dealing with indefinite integrals. And that is what these are. We'll get to other types of integrals later. So that plus c is some arbitrary constant that we don't know what is, because if we take its derivative, it will go away. Okay, so let's do the next one. Find the antiderivative of e to the w. Well, we know, because we're awesome, that the derivative of e to the x is e to the x. So guess what the integral of e to the x would be? Well, it'd be e to the x too, with that lovely arbitrary constant. So the only real difference is that lovely 9 up there. So what do you think was going to happen if we're doing with constants, coefficients? Well, what happens with derivatives? In derivatives, we have the coefficient and it comes out front. And then we multiply to whatever the derivative is. In integrals, it's the same way. If you have some constant k of x, that constant will come out front, and then you would apply the integral. So same thing here. The integral of 9e to the w, dw tells you what variable you're finding the integral for. That 9 will come out front, and then we apply the integral. And there we are. Okay, so a lot of the rules that apply to derivatives also apply to integrals. And some of the rules apply, but they're going backwards. So for the next one, we have g of x equals 17. Okay, well, this is a little bit different, because the only way to get a constant with a derivative is if you started with an x, because the derivative of a constant is 0 itself. So the only way to do this is if the x shows up. So another way to think about this is the derivative of what will give you 17? Well, that would have to be 17x. So we can derive, pun completely intended, the formula for integrals for constants. You've got a k constant. Well, that would mean that just like before, the k would come out front, but this time, instead of an x, we would have a 1, technically. So that would give us kx and then that arbitrary plus c. So for here, the integral of 17 dx would be 17x plus c. So a lot of the rules are the same and a lot of the rules are backwards. And that is where formulas will help us. And we'll get better as we go along. Antiderivative and integral are two words that mean the same thing. The antiderivative is just a word that emphasizes integrals are going backwards. So let's do this officially, with official notation. The indefinite integral. Well, indefinite integrals have that curvy S skinny thing. Indefinite integrals just means that we're not finding a specific number for that arbitrary c. We're actually just working with that c part. So the indefinite emphasizes that plus c will be on the end. So the first thing I notice with this particular problem is that we have addition and subtraction in between. What happened when we did that with derivatives? Well, we just pulled them apart. Same thing for integrals. We can just pull them apart. All right. And now we can apply the rules for integrals that we know. Well, any constant will come out front. And so far we don't know that many rules. We know e to the x, and we know the opposite of the power rule, and we can figure out the trig. So these would be the power rule. We can rewrite the square root of x as x to the 1/2 power, and we can apply the integral power rule. So remember, the integral power rule means that we're going to go up a power. We'll be dividing this time. There we are. If we don't see a number, that number is 1, so a x appears. It's actually the same thing if you think about it. We're going up a power. The power here would be x to the 0. That's 1, right? Anything to a 0 power is 1. So that would be x to the 0. Going up a power, that means I'm dividing by 1. And x, 0 plus 1 is 1. So that does actually make sense. 5, going up a power, 1/2 plus 1 is 3/2. But when you are dividing by a fraction, you end up multiplying by its reciprocal. So instead of dividing by 3/2, I'm going to multiply by 2/3. X to the 3/2. Have our arbitrary constant. And now let us simplify. So 3/6 is 2 plus 2x minus 10/3 x to the 3/2 plus c. And there we are. Let's do another one. Okay, so now that we know the basics of integration, we're getting into some of the details. Trying to figure out the integral form of the quotient rule for derivatives is not nearly as easy as you wish it was. So instead, we're going to simplify this, if we can. If we can't simplify it, maybe it's something like the derivative of tangent or the derivative of secant, where the resulting derivative is a fraction itself. So do think about possibilities of trig if you can't simplify it. But as long as we can, go ahead. Now, in division of variables, we subtract their exponents. So that would be 4t to the 17 minus 5t. Negative 8 minus 2 is negative 10. And now we're back to the integral power rule. So we can split it up at the subtraction, pull the coefficients out front. And notice I wrote that dt every time I pull things apart. This is to remind me of what variable I'm finding the integral for. Eventually you're going to have multiple variables in the same problem, and you have to keep track of which variable you're dealing with at any one time, because you can only do one variable at a time. So that's why that's there. Also, to emphasize that we are going backwards from derivatives. Remember that derivatives, we do, one of our notations is d dt. Well, for integrals, we're going backwards, so the multiplication comes out front, and we left with the dt on the end. So it does make sense in the notation wise. So power rule for integrals, we're dividing by the up power. Minus 10 t, and then up negative 10 plus 1 is negative 9, and then the arbitrary constant. Simplify. 4 over 18 is 2/9 plus 5/9 t to the negative 9, and the arbitrary constant. These are all indefinite integrals, and when you have that indefinite integrals, you're always going to have that plus c every time. All right, let's do one more. Now there is such a thing as the chain rule and the product rule for integration, but we're not going to get there yet. For the moment, we're just going to deal with what we can. We'll get to that in Chapter 5. So for now, we're right back to where we were. We want to simplify if we can, if we have this multiplication. But if you can't, do think about possible tricks. So, first thing is I'm going to multiply. Z squared plus 1 times 2z minus 5. You can use any method you wish. FOIL has been around forever, but there are other methods like the box method, or the rainbow method. Pick one. As long as they don't specify the method, you have your options. Choose what makes most sense to you. But once we have expanded it, we can integrate. So we separate individually. We pull the coefficients out front. And we apply the integral rule. So go up a power and divide by that power. Go up a power and divide by that power. Go up a power and divide by that power. And in the last case, we don't have a variable, so the variable appears, and the arbitrary constant. There's not much to simplify here, but there is a little. And there we are. Now let's try some more complicated. How about trig? In the last two examples I said simplify, but look for possible trig. Well, now we're going to have trig to begin with. Evaluate. So the integral of secant squared. In this case, you should have an immediate red flag in your head go off, because the derivative of something is exactly secant squared. We've been doing derivatives for a long time now. Hopefully you have many of them memorized. The derivative of tangent is secant squared x. So the integral of secant squared x will be tangent, and then the arbitrary constant. So that one's pretty simple, as long as you remember your derivatives. Or you memorize your integral formulas just like you memorize your derivative formulas, and that's okay too. The next one is not nearly as easy. There is no formula, no derivative that will immediately give you a derivative of sine over cosine squared. So we're going to have to algebraically manipulate this. Well, I do know, flag in my head, that sine over cosine is tangent. So how about let's start there. If we take out sine over cosine, that'll leave me with 1 over cosine. And sine over cosine is tangent. 1 over cosine is secant. Oh, that's a bit better. The integral of secant x tangent x. Do you remember any derivative that will give you secant x tangent x? Well, yeah. And that is secant itself. So the integral of sine over cosine squared, which we can algebraically manipulate to secant tangent, will be secant, and then the arbitrary constant. So you may have to do some algebraic manipulation, but for the moment at least, we're going on the basics. The last page that I gave you, page 5, does have 2 tables of integrals, and you can memorize these if you so wish. It's probably a good idea, actually, to help you out a bit. Or you can think to yourself the way we did in the first few examples. If the derivative of sine is cosine, then the integral of cosine will be sine. You are literally going backwards with these integrals. So perhaps if you've memorized your derivatives, then you won't need to memorize your integrals. But both is also good, especially in the beginning while we're getting the hang of things. So these are the basics for the trig, and we also have the basics. We've already done e to the x. There's also the natural log, and then arcsine, arctangent, and arcsecant. And we'll get more into these into Chapter 5.